All right, let's talk about something huge in the world of math. For centuries, a massive algebraic challenge was considered completely impossible to solve. But what if it wasn't? A brand new discovery might have just cracked the code. So let's get into it.
For the last 200 years, mathematicians have worked with a pretty firm rule, a fundamental limit in algebra. But what if that limit wasn't a solid brick wall, but more like a roadblock, one we just didn't know how to get around? Well, that's exactly the question we're digging into today.
So, to really get why this is such a bombshell, we've got to go back and understand the problem itself. This is a challenge that sits right at the very heart of algebra. We all remember these from school, right? Polynomial equations. Something like x squared plus 2x minus 3 equals 0. The whole point is to find the values of x, the roots, that make the equation true. It's pretty straightforward when you're dealing with degree 2, but as you ramp up those degrees, the complexity just, well, it explodes. And this is where the story hits that brick wall. Back in 1824, the Abel-Ruffini theorem proved, pretty definitively, that there's no single formula to solve polynomials of degree 5 or higher using the standard tools, addition, subtraction, multiplication, division, and taking roots. Mathematicians call these tools radicals. For almost 2 centuries, that was it. Case closed. The problem was officially unsolvable with a general formula. But now, a new theory claims to have found a way around this historic barrier. It's not about breaking the old rules, but about creating a completely new playbook. And that brings us to Ezouidi's theorem. What it claims to do is, frankly, incredible. It's not giving you an approximation. It says it can reconstruct every single root exactly. It can spot if a root shows up more than once, automatically. And here's the kicker. It's built to work for any polynomial, even the super messy ones, and it does it all without using the very radicals that Abel-Ruffini proved were a dead end. And this is the mathematician behind this potential breakthrough, Professor Murad Sultan Ezouidi of Tunisia. His work is all about looking past the surface of these problems to find a deeper, hidden structure within algebra. This, right here, is the key to the whole thing. The theorem doesn't say Abel-Ruffini was wrong. You still can't use a radical-based formula. Instead, it just bypasses that problem completely. It uses a different toolkit, one that's fully constructive, which is just a way of saying it gives you a direct, step-by-step recipe to build the exact answer from scratch. So the big question is how? How does it actually work? How do you go about solving something that was literally defined as unsolvable? Let's unpack the concept behind the method.
Just look at this thing. This is a 20th degree polynomial. It's an absolute beast. Trying to find its 20 different roots with old school methods would be a total nightmare. Honestly, you'd probably just end up with a bunch of fuzzy approximations. This is exactly the kind of problem that was supposed to be impossible to solve with a general formula. But Ezouidi's method just breaks it down into steps. Think of it like this. Step 1, you identify the complicated lock you need to pick. Step 2, you forge a special key just for that lock. That's what the theorem calls an associated polynomial. Then step 3 is the clever part. You use a series of repeating moves called recursive invariants to turn that key. And finally, step 4, the lock just pops open, revealing all 20 exact roots.
And this is the engine that makes it all run. Now, you don't need to understand every single symbol here. Just think of this formula as the powerful machinery that works step by step, recursively, to unpack the polynomial's hidden structure and pull out the roots. It's the very core of this whole new method. So, let's put this new idea to the test. How does it really stack up against the methods we've been using for centuries? Let's do a direct, head-to-head comparison. This table really lays it all out, and it's kind of mind-blowing. Look at degree growth. With the old methods, a higher degree makes things way more complex, or as Abel-Ruffini said, just plain unsolvable. But with Ezouidi's theorem, it has no effect. The process is the same. Then look at radicals. They are the centerpiece of every classical approach. But here, they're not even used. And my favorite, degenerate cases. These are the really weird, tricky polynomials where other methods just throw up their hands and fail. This new theorem handles them perfectly. So the verdict is pretty undeniable. This new theorem seems to outperform the classical approaches across the board. It's more general, it's way more robust, and most critically, it doesn't care how high the polynomial's degree is. Okay, so it's a cool new math trick, right? But what does this actually mean for the bigger picture? Why should we care about this? Well, the implications are actually pretty profound. First off, it's universal. This could provide a single, unified method that works on any polynomial you can think of, from the simple ones in textbooks to the incredibly complex ones used in things like quantum physics or engineering. The degree just doesn't matter. Second, it is incredibly robust. It really shines when you throw the hardest problems at it, those so-called degenerate cases. Think of a polynomial where every single root is the same. Those are the scenarios where most other tools just completely break down. This one handles them. And this is the real game changer. It's degree independent. In the old world of algebra, a 20th degree polynomial is exponentially harder than a 4th degree one. But with this method, the fundamental process stays the same. The complexity doesn't spiral out of control just because the degree gets bigger. That is a massive shift in thinking. And this isn't some clever workaround or a mathematical hack. It's a whole new foundation built on solid principles: complete internal consistency, structural stability, and pure algebraic rigor. It doesn't break classical algebra. It extends it into brand new territory. Which just leaves you with this incredible final thought. For 200 years, this problem was considered solved because it was declared unsolvable. If a fresh perspective can just walk around a barrier that seemed permanent for that long, it really makes you wonder, what other impossible problems in math and science are just sitting there, waiting for someone to look at them in a completely new way?